Something strange happens when you look inside an atom, and the strangeness begins the moment certainty disappears. For thousands of years, humans believed matter must be made of tiny solid building blocks. When atoms were finally confirmed in the 19th century, scientists imagined them as miniature solar systems, with electrons orbiting a compact nucleus like planets around the sun. It seemed logical, mechanical, and comforting. But the deeper physicists looked, the more that picture collapsed. The true turning point came with experiments that were not even designed to expose the weirdness of matter. The double slit experiment first showed that light behaves like a wave, forming interference patterns when passed through two narrow openings. Later, when electrons were fired one at a time through the same setup, the result was shocking. Instead of behaving like tiny bullets, the electrons produced the same interference pattern. Even when fired individually, each electron behaved as if it passed through both slits at once and interfered with itself. Heisenberg later showed that uncertainty is not caused by poor instruments, but is built into nature. You cannot know both position and momentum with perfect accuracy at the same time. This limitation is fundamental. Classical determinism, the dream that the universe operates like a predictable clock, failed at the atomic scale. Instead of certainty, there are probability amplitudes. Instead of fixed paths, electrons behave as if they explore all possible paths, and the final result emerges from interference between those possibilities. Feynman called this the central mystery of quantum mechanics, and he meant it seriously. Inside the atom, there are no hard surfaces in the classical sense. Atoms are mostly empty space, held together not by physical contact, but by electromagnetic forces. What feels solid is resistance created by fields interacting, not matter pressing against matter. The deeper one looks, the less substance one finds, and the more mathematics dominates the description. By the end of the first investigations into atomic structure, reality no longer resembled a machine. It resembled a probability system, evolving under strict mathematical laws. When two particles refuse to be separate, if superposition challenges certainty, entanglement challenges separation. When two quantum particles interact, their wave functions can merge into a single mathematical description. After this interaction, they can no longer be described independently. Even if they move far apart, their properties remain correlated in a way that classical physics cannot explain. Measuring one instantly determines the corresponding property of the other. Einstein objected strongly to this idea because it appeared to violate the principle that nothing can influence another object faster than light. He suggested that perhaps hidden variables predetermined the results. However, John Bell later derived mathematical inequalities that any local hidden variable theory must satisfy. Quantum mechanics predicted violations of these inequalities, and experiments repeatedly confirmed those violations. The results showed that the correlations predicted by quantum mechanics are real and cannot be explained by classical local realism. This does not mean that information travels faster than light in a usable way. Rather, the entangled system is best understood as a single entity described across space. Measuring one part reveals information about the whole. At the most fundamental level, space does not guarantee independence. What we interpret as separate objects may in fact be expressions of deeper unified structures. The reason we do not see obvious entanglement in everyday life is decoherence. Quantum systems are extremely sensitive to environmental interaction. The moment a system interacts with surrounding particles, the delicate phase relationships that allow interference become distributed into the environment. The quantum system appears classical because it becomes entangled with countless other degrees of freedom. The classical world emerges from quantum rules applied at enormous scale. In quantum field theory, this picture becomes clearer. Particles are excitations of fields that extend throughout space. When two particles are entangled, it is not two tiny objects communicating mysteriously. It is one extended system expressing correlations. Space appears fundamental in daily life, but at quantum depth, it may be secondary to the structure of information. The universe is less like a collection of individual things and more like an interconnected web of evolving relationships. What is really inside the atom? The final shift occurs when we stop asking what particles are made of and instead ask what they truly are. Modern physics describes electrons, quarks, and photons not as miniature objects, but as excitations of underlying quantum fields. These fields are present everywhere. An electron is not a bead traveling through empty space. It is a vibration in the electron field. Like a ripple on water, the ripple is not separate from the surface itself. This framework explains why all electrons are identical. They are not manufactured units, but recurring excitations of the same field. Matter remains stable because the properties of these fields are fixed and consistent. The forces between excitations create structured systems such as atoms and molecules. The apparent solidity of matter arises from electromagnetic interactions and quantum principles like the Pauli exclusion rule, which prevents certain particles from occupying identical states. What feels solid is a manifestation of quantum constraints, not compact substance. The wave function remains central to this description. It evolves smoothly according to Schrödinger's equation until interaction with a measuring system produces a definite outcome. Interpretations differ on how to understand this transition. Some propose multiple branching realities. Others suggest fundamental collapse mechanisms, and some maintain alternative hidden variable explanations. Despite the interpretational debate, the mathematical formalism works with extraordinary precision. Quantum electrodynamics predict experimental outcomes to astonishing levels of accuracy. Energy inside atoms is quantized, meaning it comes in discrete levels. Electrons do not slide continuously between energies, but jump between allowed states, emitting or absorbing photons with specific frequencies. These quantized transitions give rise to atomic spectra and ultimately to the chemistry that shapes the physical world. Everything from stars to living cells depends on these rules operating consistently. When one steps back, the conclusion is unavoidable. The atom does not contain tiny solid components in the classical sense. It contains dynamic fields governed by probability amplitudes. Certainty appears only in interaction. Separation is not absolute. Stability emerges from deep mathematical structure. Feynman emphasized that while we may not possess intuitive images that make quantum mechanics comfortable, the equations describe nature faithfully. The strangeness is not a flaw in the theory, but a feature of reality itself. Something strange happens when you look inside an atom, because reality at that scale is not built from solid objects. It is built from structured possibilities, interacting fields, and precise mathematical laws. The deeper one examines matter, the more it dissolves into process rather than substance. Yet from those processes emerges the stable world we experience. That is not a contradiction. It is the layered nature of reality, and recognizing that layered structure is what makes the atomic world both unsettling and profoundly beautiful.